the radio signals from space are extremely weak. So that's why, for research purposes, we use giant reflectors like the 76-meter telescope at Jodrell Bank behind me. We can't really dedicate telescopes of this size for student use, but what we can do is look at stronger sources, like the galaxy in M33, rather close by to us, and for that study of strong sources, we can use smaller telescopes, like the 6.5-meter telescope behind me. We've outfitted this telescope with professional-level equipment, and it's perfectly capable of studying the galaxy M33 and indeed of weighing the galaxy, and this is the project for you. The weak signals from the galaxy hit the dish surface and are picked up by the feed horn in the center. They're then sent round to the back of the dish, where they're intercepted by a very sensitive transistor amplifier, and the amplified signals are sent into the cabin behind me, where they're further processed, and that's where your work starts.
Okay, Emma, what have you got there then?
Okay, the receiver splits the signal into 64 bands across here. Here's one of them. Each band is 62.5 kilohertz wide. This spectrum we're looking at here is of our galaxy, the Milky Way, and it's split into two components. This frequency here corresponds to the frequency that hydrogen emits at when it's not moving. This is hydrogen's rest frequency. But because we're looking at this longitude here, we're looking at hydrogen that's towards the centre of our galaxy, so we're getting hydrogen that's moving faster than us and moving slower than us, so we're seeing a split profile. If we look at another longitude, that's 90 degrees, we see the profile much fatter, and it's become more one component. And then we also have, this is at longitude 200 degrees, and we're only seeing hydrogen here that's further away from the centre of the galaxy than we are, so we're only getting one component of the emission.
I'll show you the plots again and give you an outline of the comments in the notes, which you should work through after you've viewed this sequence. Here's the data taken along the line in green, which is at 40 degrees to the direction to the centre of our galaxy, which is shown dotted. To see what it means, let's first imagine a simple case. Suppose that there were a cloud of hydrogen in the area marked with a square and numbered number 1. It's on the same orbit as us, so the Sun and the square move around together, keeping the same distance between us. There's no relative velocity, so we would receive radiation at the same frequency at which it was emitted, the rest frequency. No Doppler shift. But look what was actually observed, and we see that it is split in two. So there were at least two clouds at different distances, and because of the differential rotation, cloud 2 is going faster than us. That is, the distance from us to cloud 2 is increasing, so we see a red shift. Whereas we're catching up, cloud 3, decreasing distance, blue shifted. The blue line shows the direction of the longitude of 90 degrees, which corresponds to the direction that we're travelling in. So we're closing in on the cloud shown as number 4. And the observations do indeed show a marked blue shift. What about the 200-degree plot? This shows a small shift. This direction is close to the radially outward direction, which would be 180 degrees. In that direction, clouds in circular orbits are running parallel to us, so they would have zero radial velocity relative to the Sun. It's not surprising, therefore, that the Doppler shifts observed at 200 degrees are small. Look at cloud 5. In TV6, you see data from a complete set of directions, and they combine to show a clear pattern. But even astronomers find it very difficult to turn that pattern into a map. So we're not expecting you to do any difficult calculations on these data. We want you to see the principles involved. The difficulties in making maps arise because we're inside our own galaxy. Turning now from our own galaxy to other galaxies, such as M33, we find it much easier to draw definite conclusions from the data. Let's join Stuart and Emma again.
Should we compare that velocity width with the galaxy that we observed last night?
You mean M33?
Yes.
Well, that's here.
What's that spike there?
Well, I think that must be local hydrogen that we failed to subtract completely, but it's quite useful because it allows us to show where the zero of hydrogen emission is. But the actual scan across M33 is very nice. All we have to do now is remove this low level of noise, which increases at a regular interval as the frequency increases. So if we judge that, we can measure the width of M33
We only need to count the number of channels.
in frequency. So 1, 2.
It's about 15.
15, 16, I think 16 actually,
Yeah.
yes. And how wide?
62.5 kilohertz.
That allows us to work out the direct width of M33. So how does that compare with local hydrogen?
Well, this is only about 3 or 4 channels wide.
So why is that
There's
so much
much
narrower?
less of a velocity spread there. The hydrogen is moving more or less at the same velocity in this case.
So the hydrogen line emission from M33 is drawn out into a broad band by the rotation of the entire galaxy. But that whole band is displaced sideways from the rest frequency. Why do you think that is? Read off the displacement in megahertz, either from the plot on the screen or the diagram in the notes, and make sure that you can explain this displacement before going any further. Check your answer by looking at the notes. Now, let's look at the broadband itself. The width of the band in megahertz is a difference in frequency corresponding to the difference in radial velocity between the approaching side of the galaxy and the receding side. First, convert the frequency width to a velocity width. The notes explain how. Now we see the effects of the orbital rotation thanks to the fact that the galaxy is tilted. And notice that the image looks elliptical, but it's a spiral galaxy, so we must assume that it is in reality circular, not elliptical, and that the tilt has turned the circle into an ellipse. If you're not sure of that, take a dinner plate at arm's length and tilt it slowly towards you. In fact, if you do that and look carefully at the shape you see, you may even be able to guess the tilt of M33. But we give you the angle in the notes and the corresponding factor by which you multiply to get the true orbital velocity in the plane of the galaxy. Now, that's already interesting, but we can go further if you're prepared to take 2 things on trust. The first is the distance of M33, found from other work to be about 2.5 million light-years. Now, if we superimpose the angular scale of the photograph, you can estimate the radius of the visible image in seconds of arc. Try that now. There's some judgment involved, but make your best guess. That's what astronomers do too. Multiplying the distance by the angle, using the proper units as explained in the notes, gives the radius. Now comes the second assumption. It relates to the band edges where the frequency shifts are greatest with respect to the centre of the band. Clearly the centre of the band is associated with the centre of M33, but we'll also suppose that the frequency shifts at the edges of the band correspond to material at the edges of the visible image of the galaxy. In other words, to the orbital radius that you've just worked out. Is that a reasonable assumption? Well, there's a lot bound up with that assumption, which we'll go through in the notes. But given that assumption, all you have to do now is to apply Newton's law of gravity in the form given in the notes. And if you manage to do that, you'll have weighed a galaxy.